All right. Good morning, Math 31s. So, we have now been working on adding some evidence into our curve sketching. So, you've looked at behavior around intercepts, behavior around asymptotes, behavior around symmetry. Now, we're going to rely on something that we already know, and that is our min-max values. Our critical numbers to find min-max points from extreme values, but we're going to go a little beyond that today, and we're going to talk about concavity and points of inflection. So when we're talking about concavity, any graph of f or portion thereof that lies above its tangent line is called concave up. Any graph G or portion thereof that lies below its tangent line is called concave down. So that's kind of a weird description, but you can think of it like this. Anything that's going like that, where it's lying below its tangent line, is concave down, and anything that's curving up is going to lie above the line, so it's concave up. All right. So when we're talking about concave down or concave up, we can have a parabola, and in this case, this is concave down, and this is concave down, right? Because here or here, both times the tangent lines, you're below, right? So when we're talking about concavity, we're adding more evidence into what our graphs look like. So when we talk about a point of inflection, the point of inflection is where the graph changes from concave up to concave down or concave down to concave up. All right, so that's a change in concavity. Concave up, since the slopes change from negative to positive, the second derivative has to be greater than 0. In other words, the slopes are increasing. Okay, so when we're dealing with concave up, the second derivative is bigger than 0. And anytime we're dealing with concave up, we're dealing with things that concave up. So like it says there, kind of holds soup. It kind of makes like a bowl shape. So anytime that it's creating like a concave up, it's, I guess you could say, holding soup, but it's like kind of makes like a bowl shape. Concave down is where the slopes change from positive to negative. So where we're now going in a negative direction of my slope. In other words, the second derivative is now less than 0, and the slopes are decreasing. So concave soup, dump soup in your lap, or obviously it just wouldn't hold anything at all. So concave up, kind of bowl shape, concave down, upside down. So this leads us to test for concavity. So when we're dealing with the test for concavity, it is just like what we were doing with our min-max values, except for now we're dealing with second derivatives instead of the first. So there will be an inflection point at any point where the f double prime or second derivative of f changes sign. So we're going to start with good old x cubed. So when I talk about x cubed, we can say, all right, well, my first derivative is x squared, and my second derivative is 2x. So when we're thinking about our min-max values, so when we dealt with min-max, then we only have one critical number, and that's 0, right? So in this case, when we looked at this from a min-max, we said negative infinity to 0, and we said 0 to positive infinity, and we just had our x squared, which is positive, positive. Therefore, our function, our derivative here is positive, positive, and therefore my original function is increasing and increasing. No, it's not. Sorry about that. Fix, abort. So when I look here, it's going to be positive. It's going to be positive. When I put the critical number in, sorry, sometimes I have to think here early morning. So when I put the negative number into my second derivative, I get increasing and increasing. So this should be a decrease to an oh no, because that is absolutely correct. I was for some reason thinking of my x squared. No, we know our graph goes like this. So x cubed, it's increasing when I'm left of 0, and it's still increasing when I'm right of 0. So with my original function. So I look at the first derivative, increasing to increasing would tell us that there is no min or max, because it's just increase, increase. So there's no increase to decrease or decrease to increase. So now if I think about the second derivative, well, the critical number here is still 0. So I still have negative infinity to 0 and 0 to infinity. But now I'm going to put it into 2x. When I put a negative value into 2x, it's going to give me a negative, and a positive is going to return me a positive. So my second derivative here is negative and positive, which now means my original function of x, this is negative, so it's concave down, and this second derivative is positive, so it's concave up. So we can see here that to the left of the 0, it's concave down, and to the right of the 0, it's concave up. Now when there's a change in concavity, concave down to concave up, this means that there is an inflection point that's happening at 0. So the inflection point is 0, and we sub this back into the original function. So 0 cubed is 0. So where there's a change in concavity from concave down to concave up or vice versa, that is what is called the inflection point. Okay, so that is the inflection point of that graph. So adding evidence onto those values in this case are going to be changing up. So we're still going to be using our evidence of asymptotes. We know this one would have none. We're still going to use our evidence of intercepts, but now we're adding in more evidence into these graphs so we can accurately sketch them. All right, so on to the next example. So this one here, the exact same thing. Now draw the graph of f of x equals x to the power of 4 minus 8x cubed using only intervals of increase and decrease and concavity. So the intervals of increase and decrease, that's what we were doing in our extreme values. So if we look at our first derivative, we have 4x cubed minus 24x squared, and I'm going to factor this. So I take out a 4x squared, and it leaves me with x minus 6. So my critical numbers are 0 and 6. So I'm looking for intervals of increase and decrease. I now have negative infinity to 0, 0 to 6, and 6 to positive infinity. And within there, I'm also going to now include my factors. So I have 4x squared and x minus 6. So I put in values. So I put a negative in here. A negative squared is positive times 4 is positive. These are all going to be positive. Then when I put a negative in here and take away 6, it's negative. When I put a number between 0 and 6 and take away 6, it's negative. And a value over 6, take away 6 is positive. Therefore, my derivative here is negative, negative, positive. So therefore, my original function here is decreasing, decreasing, increasing, which means that decrease to an increase is going to have a decrease to increase is going to be a minimum at 6, and I'm going to put 6 back into my original function. F of 6 equals 6 to the power of 4 minus 8 times 6 cubed. That's a huge question. I'm definitely going to have to use a calculator here, but punch that in, and f of 6 equals negative 432. All right, so that's our first evidence. Now, our next evidence is our second derivative. So I take that first derivative, and I'm going to the first derivative, 4x cubed minus 24x squared. Now I get 12x squared minus 48x as my second derivative. I'm going to take out a 12x, which gives me x minus 4. So now my critical numbers here, x equals 0 and 4. So when I make my chart here, I have negative infinity to 0, 0 to 4, and 4 to positive infinity. And I have 12x, x minus 4 is my factors. So a negative times 12 is negative. Positive times 12 is positives. Here, a negative take away 4 is negative. A value between 0 and 4 take away 4 is negative, and a bigger number is positive. Therefore, my second derivative is negative times negative is positive, negative, positive, which means that this graph has a concave up, concave down, concave up, which when we have a change from concave up to down or down to up, it's an inflection point. So I have one at 0 and something and 4 and something. So now I'm going to sub those values in. 0 is easy, into my original function. 0 to the 4th minus 8 to the power of 0 to the 3 is 0. And then 4, if I have to go f of 4, so f of 4 equals 4 to the power of 4 minus 8, 4 to the power of 3. So when I plug that one in, it's going to give me negative f of 4 equals negative 256. Okay, so we have negative 256. Now, can we draw this with this evidence? Okay, so we know we have an inflection point here at 0, 0. That's going to be an inflection point. We know that we have everywhere between negative infinity and negative 0 is concave up. All right, so this is all concave up here. Now we have a change in concavity at 4. So 1, 2, 3, 4, and negative 256. So what's going to happen is this was concave up. Now it's concave down. So there's an inflection point here. So we have an inflection point there and there. And then now it's going to be concave up from 4 to infinity. So the rest of this graph. But at 6 and negative 432, we have that minimum. So it's going to go down here, and it's going to stay concave up, and then it's just going to continue on forever. Okay, so what we have here is we have a minimum value at 6 and negative 432. We have an inflection point at 4 and negative 256. We have an inflection point at 0 and 0. We have it concave up from here to here. We have it concave down from here to here. And then we have it concave up from here to the end. And if you're thinking of r decreasing from negative infinity to 0, so this whole arm is decreasing, and then it's still decreasing from 0 to 6, all the way down to here. And then it's increasing for the rest of the way up. Okay, so that is what our graph looks like using all our rules of increase and decrease and concavity. Could you find where that other x-intercept is to add a little bit more evidence? For sure you could. You just have to factor out an x cubed here, and you'd have x minus 8. So you have an x-intercept at 0 and 8. So that point would be at 8 and 0 is that x-intercept. So if you needed that other piece of evidence, we could definitely add that on as well. All right, so these polynomial graphs that we talked about in Math 30, for these, we had to use our calculator. Now we can take these polynomial graphs and do a lot of work without the calculator. All right. Next example here is one where we're going to have to use a bit of a trickier derivative, right? Because we have a quotient rule going on here and we have some asymptotes. But this isn't actually asking us to do anything other than discuss with respect to concavity. So we're not asking you to sketch this one or talk about the asymptotes or talk about anything like that. All we're asking you to do is talk about where is this graph concave up and where is this graph concave down, which means we need to go straight to our second derivative. So our first derivative, low, d high minus high, d low, draw a line, square below. So when I look at this, I have x squared plus 1 minus 2x squared, which gives me negative x squared plus 1 over x squared plus 1 squared. There is my first derivative. Okay, so you could think of this as this is my first derivative. So now I'm going to have to do the second derivative. So now this is one's going to get a little uglier. So now I have to do, again, low d high, which is negative 2x, minus high, which is negative x squared plus 1, to the derivative of the low, which is 2x squared plus 1 lowered by 1, now derivative of the inside, which is 2x, some chain rule mixed in there, and then square below. So now I have x squared plus 1 to the 4th because I'm squaring something that's squared. So now I need to clean this up. Now, in order to clean this up, I'm going to do a little bit of factoring here. So I'm going to factor out a negative 2x x squared plus 1 out of this. Okay, so a negative 2x x squared plus 1. So when I factor that out of the top, all that leaves me for my first is x squared plus 1 minus. Now in the second one, it's going to take out my x squared plus 1, and it's going to take out the negative 2. So it's going to leave me with a negative of a negative, so that's going to turn this into a positive. So the 2x is now gone, the x plus 1 is now gone, so I have 2 and negative x squared plus 1 left. And that is all over x squared plus 1 to the power of 4. Now I can further clean up that top, so I can expand this in. So I have negative 2x squared plus 2. So x squared plus negative, so on the outside I have, I'm going to head up here now. So I have negative 2x bracket x squared plus 1. And then I have in my brackets, x squared minus 2x squared is negative x squared. And then 1 plus 2 is plus 3 over x squared plus 1 to the 4th. So now I can actually cancel one of these off. And then I'm done. So then when I cancel one of those off, my second derivative is equal to negative 2x, negative x squared plus 3 over x squared plus 1 cubed. So now I have to look at my critical numbers of this. At the bottom, there's going to be nothing that makes this undefined, right? When I put a any value in there, there's no way I can make that a -1 out of the x squared. So there's no value that makes this undefined. So all I have to do is look at the top. So I have a critical number of 0 here. And now I have -x² plus 3. What makes that equal 0? I minus the 3 to the other side. -x² equals -3. Divide by -1. X squared equals 3. So now I have plus and minus the root of 3. So with my critical numbers now, I have to make my chart. So I have to go from negative infinity to negative root 3, negative root 3 to 0, 0 to positive root 3, and then root 3 to infinity. Those are all my boundaries. Now my factors are negative 2x, 3 minus x squared. A little easier to think about it if you flip that. And then the last one is the denominator, which x squared plus 1 cubed. Okay, sorry about that, it's getting small. Running out of room. So here, put a negative into my x and times it by -2. It's going to be positive. Put between 0 and negative root 3, negative times negative is positive. Here, positive times a negative is negative, negative. Here, when I put a value in to x squared, it's going to be a positive, but I have to think about the number. So something that is between negative root 3 and negative 10, let's think about negative 10. Negative 10 squared is 100. 3 minus 100 is definitely negative. Here, I'm going to put a -1. Negative 1 squared is 1. 3 minus 1 is positive. Here, I'm going to think about 1. 1 squared. So 3 minus 1 is positive. And then let's think about positive 10 squared is 100. 3 minus 100 is negative. And then the last one, they're all going to be positive. Because when I square something and add something to it, it's always going to give you a positive. So therefore now, our second derivative is positive times the negative is negative. Negative times the positive is negative. And then all positives. Negative times positive is negative. Negative times positive is negative. And then the last one, negative, negative, positive. Positive times positive is positive. So it is concave down, concave up, concave down, concave up. So it's asking for, with respect to concavity, so therefore the function is concave down from negative infinity to negative root 3, or from 0 to root 3, and is concave up from negative root 3 to 0, or root 3 to infinity. All right, so long question. A lot of that derivative work comes back. Once we get the derivative work, then we're just analyzing our concavity, very similar to how we were doing max and min values in our domain and range. All right. All right, guys, last example here. So in this one here, discuss the function f of x equals x to the 1/3, x plus 3 to the 2/3 in terms of max and min values, intervals of increase and decrease, and intervals of concavity and points of inflection. Use the above information to draw a rough sketch of the function given that. All right, so what is this telling me? What we have done here is, because we don't want you to always spend the whole amount of your time working on our old derivative rules, and we've already tested that, at times we will give you the derivatives already, because now we can focus on doing our new skills as opposed to just continuing on with practicing our derivative rules, right? So with this question here, and when you looked at that question, you're like, oh my God, am I going to have to do those derivatives? Sometimes you will, but in this case, they're done for you. So I'm going to start off with my max min values and our intervals of increase and decrease. So I have to start off working with my first derivative. So when I look at my first derivative, I need to look at my critical numbers. So when I think about my critical numbers, I have the numerator. What's going to make that 0? So x equals -1 is 1, because -1 plus 1 is 0. 0 divided by anything is 0. Now, if x to the 2/3 was a 0, do the cube root of 0, 0. The 0 then squared is still 0. 0 times anything is 0. So x also, one of our critical numbers is 0. And then in the brackets, x plus 3. If I put a -3 into that, -3 plus 3 is 0. 0 cube rooted is 0. So we also have -3. So my first, when I'm dealing with those, I'm going to say, all right, well, now I have -infinity to -1. I have -1 to 0. Oops, no, I forgot about my -3. Back up. So I have -infinity to -3. I have -3 to -1, -1 to 0, and 0 to positive infinity. Now when I look at my intervals, I have x plus 1 on the top. I have x to the 2/3, and I have x plus 3 to the 1/3. All right, so when I put in -10 into x plus 1, it's negative. -2 plus 1 is still negative. Put in -1/2 plus 1 is positive, and 10 plus 1 is positive. Now, remember, x to the 2/3 is the same as doing the cube root and then squaring it. So when you square it, it doesn't matter what you do, they are all going to be positive. And this last one is the cube root of. So if you cube root a negative number, it's still cube rooted. So we have to think about this. -10 plus 3, cube rooted is negative. -2 plus 3 is positive, so cube root of positive. This one's going to be positive, and this one's going to be positive as well. So when I look at this now, I have when I'm talking about my f of x, I have a negative times a positive is negative. Negative times a negative is positive. Negative times positive is negative. Negative times positive is negative. All positives, all positives. So my original function is increasing, decreasing, increasing, and increasing. So we now have our intervals of increase and decrease. This also leads us to our max and min values, an increase to a decrease and a decrease to an increase. So the increase to the decrease, going up to down, is a max at -3 and something, and the decrease to the increase is a min at -1 and something. So now I have to put these back into my original function to calculate these. So when I put these back into my original function, now -3, so if we look at this and say f of -3, I go negative the equals the cube root of -3 times -3 plus 3 to the 2/3. This turns into 0. When 0 multiplies out, f to the -3 just equals 0. So I have a max at -3 and 0. Now the min, -1. So I have f of -1 equals -1 to the 1/3, or cube root of, times -1 plus 3 to the 2/3. So -1 cube rooted is just -1. And now I have -1 plus 3 is 2. And then I have 2 to the cube root squared. So what I'm left with here is -1 times cube root of 4, which is just negative cube root of 4. So this is my min, negative cube root of 4. So I now have my max and min and my intervals of increase and decrease accounted for. Okay, so we have increase and decrease. If we mark these off, so my max and min we have here. We have my intervals of increase and decrease, which line up with these. And now we have to worry about the intervals of concavity and points of inflection. So now I have to start all this work over with my second derivative. Okay? So now there's no critical number from the top. So I think about the bottom. This one here, it's going to be 0 again, right? Because 0 to the power of 5 cubed rooted is still 0. So we have a critical number at 0, and we still have one at -3. -3 plus 3 is 0. So we only have 2 critical numbers here. So we have -infinity to -3, -3 to 0, and 0 to infinity. All right, so when I look at this, -2 at the top, always negative. Now when I put a negative into x to the 5/3, so think about this, any negative value, cube rooted is still negative, to the power of 5 is still negative. So that one's negative, and this one is going to be positive. And then this one is x plus 3 to the 4/3. So if you think about it, you're going to do it to the power of 4 on the inside. Anything to the power of 4 before you cube root it is always going to be positive. So these are all positive. So now when we analyze this, our second derivative here is negative times a negative times a positive, negative times a negative times a positive, negative times a positive negative, negative times a positive is negative. So we have concave up. Sorry, I'm running out of room here. So we have concave up on that interval, concave up, concave down, and now we have one inflection point at 0. So when I think about f of 0, that has to be the inflection point, which is a nice one to put back in because we already know that when you put 0 back into that original function, the cube root of 0 is 0. Therefore, f of 0 equals 0. So we have an inflection point at 0 and 0. So we have all the information. Now it says use the information to draw a rough sketch of the function. So now this is where this stuff gets a little tricky. We have to now put this all together into a picture. All right? So when we're putting this all together into a picture, we know we have a max at -3 and 0. This is a max, -3 and 0. We know we have a min at -1 and -√4, which is just a little bit past 1. So this is a min here. And then we know everything left of -3 is concave up. So if this is a max and it's concave up, it's going to look like that. Now, everything between -3 and 0 is also concave up. So here, I'm going concave up and then still concave up to 0. Now, everything from 0 to infinity is concave down. So this inflection point now switches to concave down. All right, so this 0 and 0 is our inflection point. All right, so this here, we know, -3 and 0. We know that this min is -1 and cube root 4. And we know that this inflection point is at 0 and 0. So if you can now double check your increasing, decreasing, -infinity to -3, it's increasing, it's going up. -3 to -1 is decreasing, it's going down. -1 to 0 is increasing. And on the other side of 0, 0 to infinity is increasing. So this is what our picture somewhat looks like. So some of these crazy pictures, there's no idea we would have had as to what that function looked like before. If I asked you to graph that in Math 30-1, probably would have seen some tears. All right, so evidence, putting everything together. Now, this assignment is going to take you a little bit longer because there's a lot more work that happens here. So this assignment here, probably going to give you also tomorrow's class as well, which also gives you a catch-up day here. So I'm going to take a look at things, but I want you working on this. You made through these videos today, and then tomorrow is today's Tuesday, tomorrow's Wednesday. So probably get this done tomorrow, and we're probably good for the week. So we'll talk about this here, but so Wednesday's class, take a look at these notes. If you have time to try the assignment, go for it. And then Thursday, work on this assignment. And then after Easter, we're going to continue on to the second derivative test, some other asymptotes, and then go from there. All right, so we're about half done this unit now, so we're moving along here pretty good. All right, guys, you're doing awesome. Keep it up here, and I will touch base with you guys here again shortly.